Okay, so let's begin our section on thermodynamics. The first thing we want to talk about is internal energy, which we talked about at the end of the momentum section. We want to add in a new definition to the end of that. The internal energy is going to be the sum of the kinetic energy and potential energies of an object's molecules. Okay, so not the object itself, but all of the molecules. And of course, we know from chemistry, all of the molecules, whether it's solid, liquid, or gas, are always in motion. So they're at least vibrating next to each other, if not rolling over the top of each other and stuff like that. And of course, internal energy, as we've said before, um, can be caused by friction. We can release energy from a system in the form of sound, heat, and light. And all that's because we're increasing the internal energy of the object. So a good example of that is, if you pull a piece of nail or a nail out of a piece of wood, that nail is going to heat up. If you were to like grab onto the end of that piece of nail right after you pull it out, the friction that it experienced as it was being pulled out of the wood raises the internal energy of the object, which is going to be released as heat to the environment. All right, so let's talk about some vocab here. We have a system and we have an environment. Okay, so a system is a set of particles or interacting components that are considered to be a distinct physical entity for the purpose of study. And then environment is any conditions that would affect your system. So you could say the Earth is its own system. And then the environment would be the sun. The sun can input energy into our system. And in fact, it's because of that input of energy that all processes on Earth are able to occur. This explains why evolution happens. This explains um, where we get all of our energy for photosynthesis to occur, and why we can have all of the different species of life on the planet that we do. So all of that comes back to systems and environments and our laws of thermodynamics, which we'll get to here in just a little bit. Okay, so let's talk about the molecular theory of a gas. In a molecular theory of gas, we're going to pretend like we have ideal gases. And remember, in ideal gases, everything is perfect. In other words, they behave according to the postulates from the kinetic molecular theory that we learned in chemistry. We're going to just focus in on a couple of those postulates from the kinetic molecular theory. One of them is that there's no loss of energy upon collision. In other words, they are elastic collisions, okay? And we remember that from our momentum section. I hope that elastic collisions are going to conserve momentum, and they're also going to conserve kinetic energy. So when the molecules of gas hit each other, or they hit the walls of the container, they're not going to lose energy. All right, so their speeds are going to basically either be, if they're hitting the wall of the container, then their direction is going to change. So that's how the velocity changes, so that momentum is conserved. Or if they're hitting each other, other gas molecules, if those gas molecules are moving at exactly the same speed when they collide with each other. So if I had gas molecule, A, and I have gas molecule B over here, and they're both heading towards each other with equal magnitude, once they collide with each other, then they're going to move off in opposite directions, and they're going to have the same velocity as they did, previous, because it was equal. So in order for them to conserve momentum, they just need to change direction. However, if gas molecule A is moving at gas molecule B with a much greater velocity than B is, and of course, and we're going to assume, by the way, that their masses are equal in the scenarios that I'm describing right now. Okay, if the masses of those gas molecules are equal, then they're going to have to trade velocity magnitudes with each other so that momentum is conserved. Okay, or Finally, if you change the mass of both of these so that they're not the same anymore, then you'd have to go through your conservation of momentum formula to figure that out. But that's on a particle by particle basis, which we can't really do. I mean, if you were to try and figure out the momentums of every single atom of a gas in a sample, I mean, it would take a supercomputer to work on something of that magnitude. So we generally just like look at the average of everything, okay? Because we can't calculate individual gases. All right, so the last thing in the kinetic molecular theory that we're going to focus on is that the average kinetic energy of all the molecules in the system are equal to the temperature of the system. Okay, so the average kinetic energy of all the molecules in a system is equal to the temperature of the system. Okay, so let's say we've got ourselves a little cube here, and we've got all these different kinds of gas molecules, and they're all moving around in this system here in this box with different velocities. So shorter arrows mean smaller magnitudes, longer arrow means longer magnitudes of velocity, and they're slamming into each other. They're slamming into the walls of the container as they bounce around in here. Okay. That's going to give us some amount of energy, kinetic energy, and that's going to mean that there's a certain temperature that's associated with the gas in that box. Now, let's focus in on just one wall of the container here and talk about momentum, okay? Let's look at a side view here. Again, we're still talking about ideal gases. So if all those gases are moving around and they're hitting the sidewall of the container, and we're saying this green line here represents just this side of the box here. We're looking at a side view at this point. So these gas molecules are at any given moment in time slamming into the wall of the container and then moving off in some new direction as they hit and move away. Okay? So that means at any point in time we are making contact with the wall. All right, so we've got contact here, 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 and there. Okay, well, if you're making contact with something, if you're touching something, then what else do we remember has to be true about that situation if you're touching something or something's touching you? We must be applying a force. Remember, there's only two types of forces in the universe. We have contact force, field force, okay? So since these gas molecules are touching that wall, they're applying a force to it, and that's the force of impact, okay? And we remember, I hope, that the formula for the force of impact is the change in momentum over the change in time. So when these gases here are touching the wall and they change direction, that's a change in momentum. Because remember, a change in momentum is going to be a change in velocity. And then, of course, we're still doing this over time. So if we change velocity, and we're doing that by changing direction, then that means that we're also changing momentum because the mass, of course, of these molecules stays the same. So that change in velocity automatically means a change in momentum. All right? So if we look at that formula there, and we are again taking an average of these things, then we can say we can calculate the pressure that's being exerted by these gases, because we have a brand new formula here that says that pressure is equal to force over area. So we know we're applying a force because there's a change in momentum. So if we know, let me back up here real quick, if we know what the surface area is of one wall of that container, so let's say we're talking about this side wall of the cube, as those gas molecules are slamming into it, on average, if we know what the area of that is, then we can figure out what the pressure being generated is, because we can we have the force of impact, and we've got the area. We can calculate pressure. So remember, area again is length times width. All right, so let's look at the units. We've got kilograms, that's mass, times meters per second squared, that's acceleration. Mass times acceleration. And then we've got times 1 over meters squared. Meters squared, that's the unit for area, the SI unit. So this is newtons over meters squared. And we can cancel one of those meters there. So one of these cancels with one of these. And we get kilograms over meters second squared. That turns into a brand new SI unit called the Pascal. Remember from chemistry that we had some conversion factors for units of pressure, and so let's rewrite those. We have 746 millimeters of mercury is equal to 1 atmosphere. We have 746 millimeters of mercury is not millimeters of mercury, excuse me, torr is equal to 1 atmosphere. We have 14 pounds per square inch, or psi, is equal to 1 atmosphere. We have 101.3 kilopascals equals 1 atmosphere. And then, of course, that means 101,300 pascals equals 1 atmosphere. So, make sure that you remember and know those so that you can use those. All right, let's look at volume, okay? We know that the formula for volume is length times width times height. And if length times width is area, then we could say an alternate formula for volume is area times height, or area times some displacement. And if we measure length and width and height in meters individually, then that means that the unit for volume is going to be meters cubed. All right, so if we take our normal equation for work equals force times displacement times the cosine of theta, and we are trying to figure out a new equation for work, but in relation to gases, we would do the following. We're going to substitute force from the pressure formula, so we're going to resolve the pressure formula for force, and we're going to substitute the displacement variable, that's this one right here, from the volume formula. So we're going to resolve this for displacement and plug both of those things into our work formula. Now, this cosine of theta piece, that's going to go away because you can't take the angle between the force of impact and the displacement for a gas molecule. One, because we aren't calculating individual gas molecules, and two, because we're talking about volumes here. That's where that displacement is coming from. So again, that's too much individualized information. We can't calculate that. Everything's based off of an average for us. So if we plug in the pressure times area in substitution for force, and we plug in the change in volume over area in substitution for displacement, you can see that our areas here are going to cancel out, and a brand new formula, it's a boxed equation, for work done by a gas or on a gas is going to be pressure times the change in volume. And please, please, please remember that this is talking about volume, not velocity. Okay? All right, so let's look at these units. Again, for that work equation, it was work equals pressure times change in volume. So the unit for pressure we said was pascals, which was kilograms over meters second squared. Volume's SI unit is meters cubed. So we can see that one of these meters cancels with one of those meters. So we get kilogram meters per second squared times meter. I just factored out one of these meters here. And we know that this right here, kilogram meters per second, that's the unit kilogram, mass, Meters per second squared is the unit for acceleration. Mass times acceleration is equal to force, and we know the unit for force is newtons, which is where we get this down here. Okay, so then we end up with newtons times meters, and of course you know that a newton meter turns into joules, which is good because that's the correct unit for work. So everything works out well. Now, we took that cosine of theta out, and originally in the other work equations, cosine of theta was responsible for the direction. But we said we're not using that here, so we need a new method to come up with direction. In other words, the sign of our work. Okay, so the sign of the work is going to be based off of your change in volume part of your work equation. All right. If the gas expands, then the change in volume is going to be positive, and so the work is going to be positive. So, for example, if you look at your formula, you have work equals pressure times the change in volume. And this work formula assumes that the pressure stays constant the whole time. Right, let's write that down here, that for this formula, pressure must be constant. Pressure must be constant the whole time for that formula to be true. All right, another thing that we need to look at to better understand these two bullets here is proportion statements, which we learned last year in chemistry, but I'm going to take another look at them here, okay, on how to write a proportion statement. Okay, so the first thing that you want to do is to write the formula, okay? Then the second thing is you're going to cancel out anything that is a constant, any variable that's being held constant in your formula. You're going to cross it out. And you also want to replace your equal sign with the proportion sign, which kind of looks like the alpha symbol that we're used to, but it's actually a little bit more elongated than a normal alpha symbol. And I mean, it is kind of similar looking, so exaggerate it for yourself. All right, so if I do that, if I cancel out pressure, because we know that pressure is constant in this equation, then I can say that work must be proportional to the change in velocity. Let's do the next piece here. For number 3, if both variables that remain, and I say both here because that's specific to this equation, but you could have multiple other variables. So if all of the other variables are in the numerator, or conversely, if they're all in the denominator, they just all have to be on the same side of a fraction, then that means that they are directly proportional to each other. In other words, if one goes up, the other goes up. If one goes down, the other goes down. So here, if the change in volume increases, then the work increases, and we'll say that's a positive value. If the change in volume were to decrease, then the work would decrease. And then finally, if you have one variable in the numerator and the other variables are in the denominator, or any other variable is in the denominator, then those two variables that are on opposite sides of a fraction, the numerator or the denominator, those are inversely proportional to each other. So one goes up, the other goes down. Now I have here, this is not true. This is a fake statement here. Okay, please understand that. I'm just writing this down to show you what it would look like. If the equation came out looking like this, where work is in the numerator and the change in volume is in the denominator, then they would be inversely proportional to each other. We would say that if work increases, the change in volume would decrease and vice versa. So again, this is not true. I just wrote it down so you could see what that scenario would look like. All right, so if we come back to these two bullets here, that's why they are true, okay? If the change in volume is a positive value, in other words, it increases, then work has to increase also. And if the gas is compressed, the change in volume would be a negative number. The final amount of volume would be smaller than the initial amount. So final minus initial, we would get that negative value. So the work done is a negative value. So that means that if you have work done by the system, and remember the system is the gas because that's what's in the box there. So the work done by the gas is going to be positive, and work done on a gas is going to be negative. All right, so let's work a practice question here. An engine cylinder has a cross-sectional area of 0.010 meters squared. How much work can be done by a gas in the cylinder if the gas exerts a constant pressure of 7.5 times 10 to the 5th pascals on the piston and moves the piston a distance of 0.040 meters? All right, let's write down our equation for work done on or by a gas. And then let's look and see what we have. We're being asked how much work, so that's going to be the correct equation to use in this case. And they're talking about pressure and stuff, so obviously this is the right form of the work equation that we want to use. They gave us the pressure, okay, so we have that, but they didn't give us the volume. They gave us a cross-sectional area, and then they gave us a distance that the piston would move. Well, remember, an alternate formula for volume was area times displacement, right? And remember, areas that length times width and displacement could really be considered height. Okay, so they gave us everything we needed to figure out what the volume is. So we're going to be able to say then that the work is equal to the pressure times the area times the displacement. And again, we know that this right here is the volume. All right, so let's plug that into our calculators and come up with an answer. And we can figure out also how many sig figs we need to have in our answer. If I'm looking here, it looks as though we've got 2 sig figs in all of our given information. So coming up with 3.0 times 10 to the second. And what would the unit be for work? Hopefully you said joules. Okay. Okay, well, some vocabulary. Write that down, please. All right, ISO means the same, okay? So all of these things are talking about what is staying the same in the process. So I've got ISO volumetric, which means the volume has to stay the same the whole time. And since we looked at our work formula yesterday, it was work times the pressure times the change in volume. If the volume doesn't change because it stays the same, then what is the change in volume? So what's the work? 0, right? So no work is done on a system that's isovolumetric. Isolation, you stay alone the whole time. All right, isothermal. Of course, thermal is referring to temperature. So in an isothermal process, the temperature is going to stay the same the whole time. Now let's talk about that. We said from our kinetic molecular theory in our discussion of gases yesterday that all of those ideal gases behave according to all of the postulates of the kinetic molecular theory. And one of those postulates said that the average kinetic energy of all of the molecules in a sample of ideal gas is equal to the temperature of that gas, right? So if the internal temperature or the internal energy is, I don't know, I guess proportional to the temperature of the gas in that system, and the temperature doesn't change, then that means that the internal energy of the system doesn't change either. It's going to stay constant the whole time. So if that's true, if the energy does not change in an isothermal process, then you're not going to be able to transfer any energy. Because remember, internal energy is heat, sound, and sometimes light, right? So if the internal energy remains constant, then you're not going to be giving up or taking on any additional heat energy. Everybody with me on that? All right. Next one. There you go. Adiabatic. That's your next one. Adiabatic. Okay, so let's talk about this. We have the zeroth law here, and the zeroth law exists because it was created last. All right. They made the first and the second and the third law of thermodynamics first. But when you're creating scientific things, you've got to be like, cross your T's and dot your I's. You got to be very precise and specific with everything you say. And they forgot to say that heat and temperature exist. Okay, so they had to go back and make the zeroth law, which establishes the existence of heat and temperature, and then we could proceed forward with the other three laws which reference heat and temperature. So the zeroth law says if two systems are in equilibrium with each other, and one of them is in equilibrium with a third, then they must all be in equilibrium with each other. And so we said that the kinetic energy of a sample is equivalent to that sample's temperature, right? Same thing. So we're saying heat and temperature are two systems that are in equilibrium with each other, all right? Now, the first law says that, and it's called the principal law, because principle means one. Anyway, so it's the principal law, and it says that the internal energy and work and heat are all related to each other, and it gives us a formula for how they are related. And I believe this is a box equation. So it's saying delta U, and U stands for the internal energy. So that's the change in a system's internal energy is equal to, and Q represents the amount of heat energy, and W represents the amount of work. So it's equal to the heat energy minus the work. And then I always kind of have like a little picture here that I draw in, where we have heat on one side, and we have work on the other, and internal energy is kind of the bridge between those. Okay, so if you are going to convert heat energy into work, or if you're doing a lot of work on something and you're increasing the heat or the thermal output, then you're doing that through internal energy. You're going to either have to increase or decrease the internal energy of a sample in order to transfer energy from one side of this picture to the other side. Okay? Everybody got that? All right, let's do a question. Write that down. That right there should jump out at you. That depends on whether it's positive or negative, right? Yeah. Very good. So if you're doing work on the gas, or if the gas is doing work, that can change the sign of things, okay? If the internal energy of the gas increases by 114 joules during the process, what is the total amount of energy transferred as heat? Has energy been added to or removed from the refrigerant as heat? And will the gas's temperature go up or down, and why? Okay, so what formula do you think we should write down? Probably. All right, so it says that a total of 135 joules of work is transferred or is done on the refrigerant as it is compressed. Okay, so that's important. And then it says that the internal energy of the gas increases by 114 joules. And it wants to know what the total amount of energy is transferred to heat. Okay, so what should I do here? Not yet. Solve for. Yeah, rewrite and solve for Q. So heat then is equal to the internal energy plus the work. Now, let's talk about one more thing. This is a key part right here, and it says that the gas was compressed. What does that mean? Negative. The volume, or the change in volume was negative, which means what? What does that mean if, yeah, it's going to get smaller, but what does that mean about the sign for what? Which term? Work, okay? Remember, go back and look at our notes on the formula for work as it applies to gases, okay? Said work is equal to pressure times change in volume, right? And we said if the change in volume is negative, then the work is going to be negative because the pressure is assumed to stay constant the whole time, right? And if the change in volume is positive, then the work must be positive. So since this is compressing the gas, meaning that the volume goes down, the work number needs to be a negative number, right? So we need to come in here and we need to say that this is a negative value. Good job, Shimon. All right, so negative 21.0 joules is the amount of heat energy. Now, let's see, let's answer those other questions. It says, has energy been added to or removed from the refrigerant as heat? What do you think? All right, well, let's think about this, okay? If I've got this negative sign here, okay, what do you think that negative sign means? Yeah, it's lost, right? Okay, that's how much heat energy is lost from the system, okay, which is why a refrigerant can cool something down, okay? A refrigerator cools things down because it is pulling heat out of the food that you stick in there, and a refrigerator is really like a pump. It's called a heat pump, and it takes all the heat from inside and pumps it to the outside, which is why if you put your hand at the back of a refrigerator, it feels hot back there. That heat, it's not from the motor, some of it is, but it's from the heat energy on the inside of your refrigerator, all of the heat that came from your food items. Adam? You, through internal energy and work, the motor of a refrigerator does work. Yeah, well, it's what it's doing is it's compressing a gas down into a liquid, and then it pumps those liquids through. Like there's in the older refrigerators, there's like zigzaggy things on the back, whatever, and that transfers energy from the inside into the coolant to try and push it back the other direction to heat the coolant back up again. That's going to raise the internal energy of the coolant, which pulls energy out of the food. It's the same principle of you sweating, okay? The reason that we perspire, or one of the reasons, is so that we can cool our body temperatures down. So when you evaporate that liquid off of your forehead, the evaporation, that's work being done on that liquid when it evaporates, when it changes states of matter. And that causes a reduction in temperature. It removes heat in order to do that, and that's why you would cool down. So, all right. So the question then: has energy been added to or removed from the refrigerant as heat? And what are you going to say? Removed from. Okay. And then it says, will the gas's temperature go up or down, and why? What do you think? Down. Okay. Should go down. Very good. Did I give you an example of an adiabatic process yet? No. If anybody ever gone scuba diving or been around a scuba tank before ever? Okay. I need to bring my scuba tank up here. If you take the nozzle of a scuba tank and you just open it, open it wide up, but you hold on to the valve where the air comes out, the compressed gas, it gets really, really cold. All right. That's because what's happening is the change in volume in the tank is happening so rapidly that there's not enough time for the internal energy to change, and so it rapidly cools down. Okay? All right, write that down. All right, so let's talk about this. My turn. So the top there, entropy. Now, we didn't get to make it this far in chemistry last year, which greatly saddens me. But we have two driving forces, is what they're called, in the universe. And one of them is entropy, and the other one is enthalpy. Okay? Enthalpy is the energy of a system. And basically the standard law, of the universe says that you try and accomplish a task by using the least amount of energy possible. That's the law of enthalpy. Okay? Then you've got entropy. Entropy is a measure of randomness, chaos, and disorder. And the universe favors randomness, chaos, and disorder. So no process can occur unless one of the driving forces, at least one of the driving forces, are favored. So if randomness and chaos and disorder are favored, then enthalpy doesn't have to be. And I'll bring this back around to evolution again, okay? We know that if we're trying to follow the idea of evolution, you're supposed to get more complicated as things go along, right? So when that makes sense. We go from a single-celled organism, and then it starts getting compartments, little organelles, and that becomes more and more complex. That would take an input of energy because that's becoming less chaotic, all right? If you're becoming more organized, then you are conversely becoming less random, correct? That means that entropy does not favor evolution, which means evolution requires an input of energy in order for it to exist. And we already talked about where we get that energy from. Where's that? The sun. Very good. Okay. All right. So let's talk about the second law. The second law is basically the law of entropy. Okay. It's saying that there is no cyclic process that will 100% convert all of the heat energy into work. Okay, which is why you can't have a 100% efficient machine. And that word there, efficient, that's going to be a key word on a quiz or test. Okay, that's the one you're going to want to look for. And if I'm talking about efficiency, I'm talking about the second law. Okay, you cannot have a 100% efficient machine that completely converts all the heat energy into potential work. Okay. Because it will break the second law. This law says it can't happen. And I'll talk about why that can't happen in a little bit more detail in a second, okay? Yes, it could be a very efficient machine, but it cannot be 100. The entropy of the universe increases in all natural processes, okay? Meaning it will get more random. Heat always flows from hot to cool temperatures, okay? So if you take your hand and you put it on your desk, what does the desk feel like to you? It feels cold. That's not because the desk is cold, all right? That's because heat is flowing out of your hand right now, okay? The reason the desk feels cold to you is because your body heat is flowing into the desk. You are heating the desk up, and your nerves register that as a drop in temperature, so it feels cold to you. But there is no such thing as cold. All right, which is why when y'all say, "Ooh, it's cold in here," I'll say, "No such thing." Right? It's less hot in here than your body temperature. Okay. What?
Is that why when you like stay under a blanket, you get like super warm because you're like transferring the heat and it's like trapping the heat?
Yeah, you're keeping those heated up air molecules around you. They're kind of like insulation. The reason that the second law exists is because you can't have a frictionless environment. Okay, you cannot have something that is completely frictionless, and you can't have something that is perpetual, which means goes on forever or never ending. Some amount, yeah, it's small, but yeah, it's there. Okay. So since you can't have a frictionless environment, you cannot have a 100% efficient machine. Okay, the gears that grind against each other in a motor, that's friction, that's stealing energy. Okay, even the simplest machines, maybe you ever made a rubber band airplane or something, or a rubber band car or something like that, and it spins around. There's friction there, and that steals energy, which eventually means it can't run forever. Which is why, and this is another thing here, the second law of thermodynamics, you can use that to spot fake science. Remember, we talked about this already. If someone's trying to sell you the idea of what's called free energy or endless energy machine or perpetual motion machine, you don't even have to listen to them after that point. As soon as they say those words, they're done. It's over. Okay, they broke the law, and that law can't be broken. All right. So
what about those where it's like where you like hit one and then it like keeps on going or something like that?
That's called what is that? Newton's cradle, and there's friction in the movements of those strings, and it will come to rest eventually. Okay, so you cannot have perpetual motion. You cannot have a 100% efficient machine. All right. Finally, the third law: there cannot be a system without energy. It can be a system with a very, 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 very small amount, but it can't be zero. Okay, you cannot have a system with zero energy. All right, absolute zero is the theoretical temperature on this Kelvin scale at which there is no energy. Okay, all energy would be removed from the system at that point, and there's no motion at all. And when we're talking about no energy, I mean even the electrons that orbit the nucleus in the atoms of whatever object it is you're looking at would come to a rest. Those electrons would no longer orbit the nucleus. Okay, so that temperature is only theoretical. We've gotten very close to it, but we can't hit absolute zero. That would break the third law. Okay, so that's never going to happen. It is only an extrapolation of the data that we see. We can get it colder and colder and colder, but we can't ever get down to this point. But we can say, hey, that point still exists. We just can't ever get there. There's a little leap at the end of the data. Okay.
So when the universe dies, will it be an absolute zero?
I don't know. I don't know, because we just said that can't happen, but at the end of the universe, I don't know. Maybe all bets are off. I don't know. Adam. Okay, Josh.
So does that mean like absolute zero and no friction? It's like an asymptote. It goes all the way up and gets right next to it and it stops.
Mm-hmm. Yeah. Well, it wouldn't even stop. It just keeps going on for infinity. Yeah.
Going right next to it, getting one more.
Yeah. Yeah. Isaac. Well, energy could be part of the environment, but if I zoomed out further and said, well, now that's part of my system, I mean, it's all your perspective. We put a picture of like the Earth inside of a box and said that was the system and put the sun on the outside, right? What if I put the Earth and the sun both in the box and I said that all the rest of space is the environment, right? Any black holes or comets or something that flew by the sun, they kind of tug on the sun a little bit. That affects that system, right? So it just kind of depends. Other questions?
What would be an example of a system that's close to zero, like absolute zero?
Oh, well, anything that we wanted to do in the lab, we can force something to get, colder and colder. Trying to think. You can just super cool something, and keep getting it closer to absolute zero. But I don't know anything in nature that would be like
Well,
that.
I have a question. Isn't it like liquid nitrogen? It's got stick your hand in there and like pull it right out, and then everything's like.
Yeah, you're fine. That's because the heat of your hand is enough to vaporize the liquid nitrogen before it has a chance to give you frostbite and to hurt you. So your own body's heat is actually kind of a thermal insulator, protection for that. Now, if you just stuck it in there and left it and gave it a chance to cool you down, then it'll get you. Bram, we've been able to get, I think it's within well, it's not technically correct to say degree, but a unit or so of absolute zero. Like, we've been able to get pretty close, like almost there within, either decimal places or within like 1 unit of it or something. So.
Okay, so you would agree that like things are held together because of the electron bond, like they're spinning until they like attract two molecules.
Oh,
together.
okay. The intermolecular forces, or are you talking about individual electrons being attracted to each other because of their spin?
Everything that keeps them together.
Okay.
So like to make this table. But then if they turn 0 degrees and they're not moving at all, wouldn't that just crumple apart? So wouldn't everything?
Well, actually, that's a good question, and I think I know where he's going. If I have 2 electrons and one's got a clockwise spin, one's got counterclockwise, because we've got Pauli's exclusion principle going on there, and that causes there to be a force of attraction between electrons, because normally they would want to repel because they're both negatively charged, right? But it is their opposite spin that causes that attraction. But if they're not spinning anymore because we're at absolute zero, if that ever happened and those electrons came to rest, now it's just their repulsive forces, so they would want to repel and fly away, but they can't move because they're at absolute zero. What happens? They can't fly apart? Do they get pulled inside the nucleus to counterbalance their charge with the protons? But they can't, because they can't move into the. What happens?
A big explosion.
We don't know because we've never been there. I don't know.
You take the negative electron.
I have no idea what would happen if they came to a rest. I don't know. They can't move. It's zero. No motion.